All right, we're going to really continue the exact same idea we did before. We're going to move to some kind of outdated formulas, some identities that have kind of lost maybe their meaning. But so we're going to look at double angle formulas. And the use of this if in the real world would be you don't have some angles on your unit circle, but you see that it's twice as large as a much easier angle that you can find on the unit circle. So suppose you, I don't know, well, this isn't a good one because you could find 120, but suppose you did 120 and you didn't know that. Well, half of that is 60. So we're going to have a formula here where you could go, okay, well, I want to look up 60 on my unit circle. Well, that's why. Now, in this section, we're actually not going to do that. We're going to just primarily work with these identities. But so we've derived a bunch of identities that say, hey, I have a double angle that I want to work with. I have a double angle formula here. So all of these identities are actually just, I'm not going to go through all their proofs, it's in the book, but what's happening here is if you're just using the sum and difference formula, isn't the sine of 2 theta just equal to the sine of theta plus another theta? Isn't that just the sum of the same angle twice? So if you went through these and just use the sum and difference formulas from our last chapter and you use the same angle twice, you could just simplify them all into these. Now there's different versions of this cosine of 2 theta, but it's all just manipulating the formulas and using the Pythagorean identity. So all I'm saying is you're using the sum and difference formulas from the last section, but the two angles are the same angle. Okay, now the problem here, so I hope in the next section we'll have some simple ones where we would just have an angle that that's twice one on the unit circle, and all we're going to do is just plug it into this formula and find the value. So I hope that's in the next one, but it would be pretty intuitive. You had an angle and you're like, oh, okay, that's twice 60. I could just plug it in. But that isn't what they're going to start us with as we start this section. What we're going to do here is that we are given the fact that there is some tangent of theta that equals negative 3 over 4. They tell us what quadrant is in. Now, I don't know why I didn't paste all of this, but what they're going to ask us is to find the values of all of these double angles. They want to know the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. So, do they have the triangle? Yeah. So, we are in quadrant 2, so they've drawn us the little picture. And they're telling us that the opposite, I would have written it like this. Yeah, so this is going to be 3, and this is going to be negative 4. Now, why is that? Why does this one get the negative? So remember, tangent is opposite over adjacent. Why do we call negative 4? Because we're in quadrant 2. In quadrant 2, the x's are the negatives, so we know it's 3 over negative 4. Now, they've done us a favor here of just finishing the Pythagorean theorem, and it turns out this hypotenuse is then 5. So we've got everything we need now. We can look up, so the sine of this angle is going to be 3 over negative 4. Negative 3 over 5. The cosine of theta is going to be, I messed that up. Sine of theta here would be 3 over 5. Cosine would be negative 4 over 5. And we already knew that the tangent of theta was negative 3 over 4. Now, why do we need these? All we got to do now is plug them in to our equations. The double angle formula, if we're going to double that angle we're working with, it's 2 sine of theta cosine of theta. Well, we know these. I just got them all off the triangle we created. And we simplify. Now they want the cosine of 2 theta. Well, the formula for that was, go back here, cosine squared theta minus sine squared of theta. So I'm just plugging it in. Just plug it in. I just found these off the triangle that I completed. All I have to do is simplify. And then I can do the same for tangent. Tangent, they already told us was negative 3 over 4. I'm just plugging that into the formula. And now I know the double angle for that tangent. Do a little simplification. We get down to there. Okay, pause this if you want to try it yourself. If you don't feel super confident with that yet, that's fine. Just watch me do this here. So I'm going to build a triangle. And I'm in quadrant 1. They tell me I'm in quadrant 1. So I've got sine is, well, it's alpha here. So opposite over hypotenuse. So let's find side A. We don't know what it is. So it's a squared plus 5 squared equals 8 squared. So I've got a squared plus 25 equals 64. So a squared is going to equal 49. Am I right about that? 40? No. I was hoping it was going to be. So 39. That's unfortunate. Okay. So a squared is 39. So yeah, that's unfortunate. Okay, so we're going to square root both sides. We're going to get the square root of 39. Now a square root is a plus or a minus, but they told me I'm in quadrant 1, and a is the value of x. So it's positive square root of 39. Okay, so they actually didn't ask for all of them here. So cosine of 2 theta is it cosine squared minus sine squared first? Sorry, I got to go all the way back because I don't have it memorized. Yeah, it's cosine squared minus sine squared. Okay, so it's cosine squared of the original angle minus sine squared of the original angle. So we have our cosine squared would be the square root of 39 over 8. So cosine would be this side, which we just found, over 8. We're going to square all that. And then we're going to square sine, which would be 5 over 8, which we already knew, actually. Okay, so I've completed my triangle. Now I can find any other trig identities by their definition that I want. So I now have the sine, and I found the cosine just from it's adjacent over hypotenuse. So if we crunch this and I put it into the double angle formula, it's just a formula off your formula sheet. So I've got 39 over 64 minus 25 over 64. So I get 14 over 64. Okay. All right, this is a bit of a strange one here. So they want us to start with cosine of 6x. I guess this you could use this in identities from time to time. You'll see this trick. But they want us to write it in terms of cosine of 3x. This is all we're doing. Couldn't 6x be turned into 2 times 3x? Do you see what I mean? Cosine of 2 times 3x is 6x. So now we've got a double angle. Do you see what they've done? I've got a double angle formula where theta is going to be 3x. Okay, well, if you look up the double angle formula for 2 theta, you get cosine squared minus sine squared. And my theta is 3 over x. So that's what they've done. I've just put that in here, cosine squared of theta minus sine squared of theta. Yeah, I was like, what are they doing here? Okay, so here, what they've done is they've used the Pythagorean identity to take this one step further. Oh, I guess they wanted, okay, I guess so they wanted all in terms of cosine of 3x. So, remember the Pythagorean identity says this. If you add the two angles, you get 1. So we could get rid of sine squared of theta from the Pythagorean identity by saying it's equal to sine squared of 3x equals 1 minus cosine squared of 3x. Yeah, they didn't show any of this. So let me go over here. Yeah, this is what they're doing. They didn't show this. They're making this change from the Pythagorean identity. Now, if I'm substituting, I have to put it all in parentheses. And so this negative is going to go through here and go through here. And I'm now going to have These are two of the same thing, identical thing, so it's two of them, minus 1. Yeah, they jumped pretty quick on that. Okay, so that was basically like proving an identity, but okay, let's, now we are going to prove an identity. What we want to do here is, I think for the rest of this section, we're going to see if we can use these double angle formulas to help us prove something. So this first one they've done for us. Now I would look at this, there's two ways I could go. This screams substitution here. I know the double angle formula and I could just replace it. However, this one right here is screaming just do some basic algebra, just expand this. And I don't know which way they're going to go. You'd get there either way, but remember, we have to choose a side. You could either work the left side and see if you can turn it into the right, or you could work the right and see if you can turn it into the left. But we're not sending stuff across this equal sign. This is a proof. It's not an equation. So they went ahead with the right. So they just FOILed this out. So remember, like if you had x plus 3 times another, squared is really times another x plus 3, and you would FOIL it. Well, that's what they're doing here. Now this is a pretty common pattern, and they just kind of jumped to the pattern. But if you FOILed this out, sine of theta plus cosine of theta times another one, that's what they're doing. But if you know the pattern by heart, this is what happens. It turns into this. Now, that's a nice start, but look at this. They've rearranged it. They put the sine of theta and the cosine of theta together at the front. So basically, they've done all algebra so far. Sine of theta squared plus cosine of theta squared is the Pythagorean identity. So now we're ready to make a substitution. That's 1. And we're almost there. I've got 1 plus 2 sine of theta cosine of theta. Man, they keep making leaps here. That's not... hold on, I gotta check that identity. Excuse me 1 second here. Yeah, so they didn't show it, but what we had was 2 sine of theta cosine of theta is sine squared of theta. I should have remembered that, but I didn't. Excuse me as I scroll through all of this. Okay, so what we have here, this is the double angle formula for sine of 2 theta. Are they going to show that? No, they don't. Okay, so it's 1 plus sine of 2 theta. Because we're just substituting. That is the double angle formula for sine. So we're there. Okay, so here's another one. I was looking at this one before I started the video here. You could go choose the right and just choose to expand this. But I think there's something... I think this one is screaming, let's work with this side, because I'm seeing a perfect square binomial. So it doesn't matter that it's to the 4th power. You can do x to the 4th minus y to the 4th, and you could factor this. You've got square roots on the front and the back, and you've got a minus in the middle. So I'm going to do this. Cosine squared of theta minus sine squared of theta times cosine squared of theta plus sine squared of theta. So I'm going to work with the left, and I've just factored it, just basic factoring. Now, I look at this and I say, wait a minute, that's the Pythagorean identity, and so it's 1. This is all just the number 1. So if I substitute in a 1, it just all drops out, and I'm left with cosine squared of theta minus sine squared of theta. And if you go back, this is equal to, it's the very same thing, oops, as cosine of 2 theta. And we're there. Okay. Yeah, I was looking at, okay, this one, we want to get from tangent of 2 theta into this. Now they're going to go from the left, I believe, but I think this is much easier to go from the right, so I'm going to skip what they did here. I looked at the right and I said, well, let's see what happens. Cotangent is 1 over tangent. So I just made one substitution. I said cotangent is 1 over tangent. Now why am I doing this? I wanted to stick with all tangents because I'm looking for a double angle of tangent. Okay, so I'm looking at this in the bottom. I made a substitution. Let's do some algebra. This is like over 1. So let's get a common denominator. I want them both to be over tangent of theta. So if I did that, I'd have to add a tangent of theta over here and 1 on the top. I'm just getting a common denominator. Do you see that? I'm getting them both to be tangent of theta. You do it to the bottom, you got to do it to the top. I've got 2 over 1 minus tangent squared theta. See, I'm just multiplying that together. Now, they're both over tangent of theta, so I'm just going to put that over tangent of theta. Now you say, well, what good has this done? Well, I have a number divided by a fraction. I'm going to keep, change, flip. And what will happen there is it's going to the tangent of theta on the bottom is going to flip up to the top. We've got 1 minus tangent squared of theta. And you say, okay, well, what is that mess? Well, if you go back to our definitions of our double angle, that's tangent of 2 theta. We have it. Those are the same thing. So we got there. Okay, so again, they worked it, and you can't see it with my red, but if you're looking at the PowerPoints on your own, they went, or looking at the textbook, they took the left and turned it into the right. But I didn't like the trick that they did. I didn't think it was very intuitive. So I think it works a little easier if you start with the right. Okay. Now, I'd really recommend you just pause it, try it if you need some practice with these identities, and you can watch me. I think there's two things happening here when I look at this one. I say, okay, this is screaming, just make a substitution. I think that actually is going to be super easy as well. But I actually looked over the right, and this is the first thing I saw. These both share, they have a GCF of cosine. So I'm just going to take it out. Yeah, I think it's easy either way. But I'm going to choose to work with the right, and I'm going to factor out a GCF. They both share a cosine of theta. So I've got cosine squared of theta minus sine squared of theta. Okay, you go, well, what's next? I did some algebra. What's next? That is the definition right there of cosine of 2 theta, so I'm already done. If you look back on your definition sheet, that's cosine of 2 theta. That's what it is, so I'm already done. This is now the left side already. Okay, so we had some identities there using the double angle formula. I think all of these were pretty easy. Remember, algebra or substitution. Substitution or algebra, either way. Just do one and then see what you got if you can make a substitution. I think those were pretty easy to follow.